Hello, in this video we're going to look at Gaussian intervals, and we're going to start simple and get more complicated. And what's interesting is for our identity 2 we're going to use identity 1 to help us prove it. For identity 3 we're going to use 2 to help us prove 3, and 4 we're going to use 3 to help us prove 4. And let's just jump right in. So this first one, the integral of e to the minus x squared, is pi over, or the square root of pi. Now, if you notice, there's, sometimes a 1/2 is put here to make it look like the standard normal distribution, and then it integrates to square root of 2 pi, but there's no constant in front of that. And now there's so many videos that show the proof of this. I'm not going to prove it here, and this will be the only integral we'll assume true, but like I said, there's lots of published videos on this, so we'll assume this is true. Now the second identity, we're going to let x be a vector, and we're going to show that this integral of e to the minus and then this vector product is equal to the square root of pi raised to p. So let's start in. So this is the integral we want to show, and this right here is the sum of the squared, and over this p dimensional region we can iterate it, and that's due to Fubini's theorem. And so there are p integrals here because it's x1 through xp. And next we can break this e function apart a little bit. So we can isolate the e to the minus x1 squared and then take everything out front. And so we integrate this first, and based upon identity 1, we know that's the square root of pi. So that'll come out front, and then we're left with what's left over. But we could isolate the next one, the x squared, x2 squared term. And this would be based on identity 1, square root of pi. So that goes in. So we have it integrated two integrals, and we get square root of pi squared. And we could just keep doing this for all p variables, and we get the square root of pi raised to the pth power, and that is pi raised to the p over 2 power. So the third identity, let's let x be a vector, p dimensions, and A be a p by p symmetric positive definite matrix. We want to integrate this over the whole space, p dimensional space, and that is equal to this, where you can write it like this or like this. So it's p raised to the p over 2 times the determinant of the inverse matrix of A inverse, the square root of that. Or this can actually be taken down, and then be the determinant of A, and then that half, of course, is the square root. So let's let A to the 1/2 be a square root matrix such that A is equal to A to the 1/2, A to the 1/2. And I have quotes around this because I have a video called a square root matrix that helps explain what this is. Now, in that video, we don't really cover these properties, but based on this video, it can easily be shown that these properties are true. So the determinant of A to the 1/2, so this matrix, you can really take that 1/2 out, and then it ends up being the determinant of A, the square root of that. And then same way, since these are positive definite matrices, you can take an inverse, but that minus 1/2 can be easily shown to come out of that determinant. So let's do a variable transformation. Y is equal to a to the 1/2 x. And then we can back solve for x, and we get x is equal to a to the minus 1/2 y. Now the Jacobian of this transformation is the determinant of this, or the absolute value of this determinant, which is the partial of a to the 1/2 y in regards to the vector y, and that is this inside is a to the minus 1/2. And I have a video on taking these derivatives, matrix derivatives. So it's determinant of a to the 1/2. So now with that background knowledge, let's start. So here's the original integral that we want to integrate. Let's make a variable transformation, and we plug in a to the minus 1/2 y in wherever there's an x, and then this differential is the determinant of a raised to the minus 1/2, and then the differential of y, and these are vectors. Now when we take that transpose in, this is changed around. That since that's symmetric, it doesn't we don't need a tick there. Well, a to the minus 1/2 a to the a to the minus 1/2. In the video, a square root matrix, we show that's the identity. And now this a to raised to the minus 1/2 can be taken out of the integral because it's not part, there's no y's in it. So this right here becomes this, e to the minus and this vector product. Well, according to property 2, this was the square root of pi raised to the pth power, this. And then, so that comes out front. But then this is easily manipulatable to be what it shows. So this 1/2 we can take down. And then since there's a 1/2 in both, we can just take the square root of the whole thing. And then this is what we wanted to show. Now a quick example using this, let's let P be 1. So we're in the univariate case. And so the matrix A is actually just the number A. And the vector is just one variable, x1. And the determinant of a number is just that number. So now if we're in this case, which this can be thought of, so we're in this case, and that A can be in the middle. So it's x1, A, x1, which is the same as this. And then, so that, according to this property, is the pi raised to the 1 power divided by the determinant of A, which is just A, the square root of that. Now the interesting note is that if this were 1/2, then this looks like a standard normal distribution. So you'd put 1/2 here, and then when you invert and multiply, you get the square root of 2 pi, which is what it should be. Now let's look at our last identity. So let's let X be a P by M matrix and A be a P by P symmetric positive definite matrix. Then this integral, which at first doesn't look Gaussian, but it is equal to this. So it's pi raised to the P times M, and then the determinant of A raised to M, all under the square root sign. So we're going to spend a little bit of time evaluating this piece right here, the trace of this, I think it's a general quadratic form, because this is a matrix, this is a matrix, this is a matrix. So let's let X, we write it in these are vectors, so each column can be thought of as a P by 1 vector. The matrix A can be thought of as P columns, and each of these are P by 1 vectors, where the X's and A's are P by 1 vectors. Now we want to examine this trace. I'm going to write it out in some detail here. So this X transpose, we take this, right, which are columns going down, and we transpose it. So now these are, these can be thought as row vectors. And then of course A stays the same, and this X stays the same as that one. So now when we multiply this out, you take this piece times that, and then this times this, and you end up getting this matrix with this two matrix multiplication. Okay. Now the next one is, this is the most crucial point. So this is, remember this is with the transpose, this is a 1 by p, and this is p by 1. So this is 1 by 1. So it's a number. So we have p numbers here. And now notice that this right here is a p by 1 vector. So we take this row times this vector, right? But if we think about this here, we can left factor out an x1, and then what's left in is a matrix with A1 is the first column, A2 is the second column, AP is the pth column. So this is A1 transpose A. So we take that times this, and then this times that, and then this times this, and we end up getting this matrix here. So this piece times this first one is this, and then this times this row is this, and we go. But we're interested in the trace. Now, so each time we bring down the trace, the trace, the trace, and what is the trace of this matrix? That says add up the diagonal elements. Well, this plus the second piece, oh, that's a 2. And then we keep going all the way to m, because there's m rows, so that is the last one. So now we put that knowledge back into our integral. So we have this, the original integral we want to do, and then this we replace with what we just learned what it is, all these little quadratic forms. And then thanks to Fubini, we can iterate it. And now we focus on x1. We can kind of break this apart. So this is the the x1 quadratic form, and then everything else. And when we integrate this, thanks to property 3, we know that is pi raised to the p to the 1/2 and determinant of a to the 1/2. Right? Now, and of course we have everything left over. And we can repeat that. Now we can isolate this piece and do the same thing. So we get another one of these. And then we do that for each case. And we go da-da-da-da-da-da. So we get this raised to the mth power because of these, there's m of these integrals. Well, we take the m in, and then the 1/2 in each could be used as the square root. And this is what we wanted to show. Now this is going to come into play when if I get there. This is kind of the goal, is I want to derive the Wishart distribution, and there we're going to integrate integrals like this. So anyway, hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.